So this video is about computational tricks, or I guess computation, the division algorithm, and simple extensions. All right, so there's so here's a concrete example, or let's say a question, kind of a motivating question. So consider the polynomial here. Let's say f of x, x to the fifth plus 4x plus 2 in Q adjoin x. Okay, so by Eisenstein, uh, this is irreducible. Okay, and so we can consider, so let alpha be a root. So let's say it's in the complex numbers, be a root. And consider, here, this field f, which is Q adjoint alpha, the simple extension. Okay, so here we know that Q of alpha, right? Q of alpha. So this thing is really Q plus Q alpha plus Q alpha squared plus Q alpha cubed plus Q alpha to the fourth. So this is an inequality as Q vector spaces. Right. So in particular, we should okay. So this is what we have. So what is let's say 1 over 1 plus alpha. So this should look like so this should look like something here. So this so what is let me write it here. So what is, let's write it in red. So what is 1 over 1 plus alpha here? So here it should be an element with coefficients in this with Q coefficients, but we need to somehow separate it. So like one thing we could try, right? Okay, so like what could we try? Right, so let's try something. Oh, 1 over 1. Oh, dang it. 1 plus alpha. Okay, so one thing we could try. So you could try tap tap. Oh, tap tap again. So you could try. Oh, we'll go red. Okay, so we could try like a geometric series, right? So 1 over 1 plus alpha. So this is like the sum of n is equal to 0 up to infinity of negative alpha to the n. And then maybe you like wrap all the degrees up. So this is like here. I don't know. So you could try and write this out and then like 1 plus, or 1 minus alpha plus alpha squared minus alpha cubed plus alpha to the fourth minus alpha to the fifth plus alpha to the sixth minus, okay, and then maybe you could try and do something like, okay, every time there's an alpha to the, so every time there's an alpha to the fifth, right, we apply this formula, right? So maybe we apply every time there's an alpha to the fifth, we try and write that formula down. So like here, so this is 1 minus alpha plus alpha squared minus alpha cubed plus alpha to the fourth minus, okay, now I'm going to write, this is, okay, so an alpha to the fifth, what does it become? An alpha to the fifth becomes minus 4 alpha minus 2. So minus 4 alpha minus 2, and then minus alpha minus 4 alpha minus 2, And then you could just keep going like this. So this is plus, minus. Okay, and then so what happens is that this gets really messy. So this gets really hard, messy, and I don't even know if you can make sense of this. So maybe it doesn't even work. Okay. So another thing you could do is you could try an experiment. So you could do like, you could try and do 1 over 1 plus alpha, and then maybe we do like 1 plus alpha, so that gives you a 1. And but let's see. So actually, so we need to figure out that what 1 plus. So you could do 1 plus alpha. And you could try and write something down. You could write like a plus b alpha plus c alpha squared plus, I don't know, d alpha cubed plus e alpha to the fourth. And then we just like try and multiply this out. A plus b alpha plus c alpha squared plus d alpha cubed plus e alpha to the fourth plus a alpha plus b alpha squared plus c alpha cubed plus d alpha cubed to the fourth plus e alpha to the fifth. And then, well, then you just collect all the terms. C plus b alpha squared plus, and then you just go like this. All right, and then okay, this could work maybe. So minus or plus e, and then you have minus 2 alpha minus 2. Or is it 4 alpha minus 2? What did we decide? Minus 4 alpha minus 2. Okay, and then so then you could put these and then solve. Okay, so you do this, then solve each of the equations. So that actually would work, right? So then so let me just, I guess we could just do this to completion, right? So this is so I worry I'm gonna mess this up, but a minus 2e plus, okay, then we have the alpha term a plus b minus 4e alpha plus c plus b alpha squared plus d plus c alpha cubed plus e plus d alpha to the fourth. Okay, and so now we this thing needs to be equal to 1. Okay, so then we have, okay, a minus 2e is equal to 1. We have a, I mean, this isn't really the point of this video, right? So the point is that this is a bad idea, what I'm doing right now. C plus b. Right, that one needs to be a 0. D plus. So what I'm doing to get these equations, by the way, is I'm using linear dependence. So linear independence of those basis vectors. E plus d is equal to 0. Okay, I think that's all we have here. So we have all these equations. And then we can just solve. So you solve, right? And so and then you'll get something, right? So yeah. So this gives you an answer, right? Okay. Maybe there's kind of a better way of doing this. So here's kind of a better way of doing this. So a better way. Okay, is that so let's kind of set this up generally. So suppose f of x and f of x is irreducible of degree d, right? Then what do we do? So if it's irreducible of degree d, then here we have f of x over this. This is minus f of x. So this is isomorphic to k. So this is a simple. This is isomorphic to a simple extension, and so a general element can be written as the following. So it can be written as, so I'm going to use the bar notation. So a0 plus a1 x bar plus a2 x bar squared plus dot 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 plus a d minus 1 x bar to the d minus 1. Okay, and so so the point is that let's let g of x. Okay, so I'm going to let g of x be this thing lifted to the polynomial ring. And the point is that this polynomial and the polynomial f must be co-prime since f is irreducible, right? So f is irreducible up here. So these two things need to be co-prime, right? Since they're co-prime, their GCD is 1. And so what does this tell us? So this tells us that so f this says that the GCD of f of x g of x is equal to 1. All right, and there's a theorem that says also you can always write GCDs as a linear combination of the two elements. So also there exists two polynomials, right? So there exists some ax and bx and f of x such that, well, the a of x f of x plus b of x g of x is equal to the GCD of f of x g of x, and then which in this case is 1. In practice, when you do this, it'll be up to a constant here. Okay, so now what question were we trying to answer, right? So the question we were trying to answer was, how do we compute an inverse of a general element, right? So here I have a general element. This is a general element in K. And we want to know what 1 over g of x bar is. Okay, so what's the inverse of this? So the inverse, so 1 over g of x bar, and we want to write it in terms of, some combination. So we want to write this as C0, C0 plus C1x plus CD minus 1 XD minus 1. Okay, so we want to write it in terms of the basis. Okay, so what is this? So it's the unique element. So this is the unique element such that, well, let's say the unique element such that, well, g of x bar times 1 over g of x bar is equal to 1. So we just need to find some element such that g of x bar times 1 over g of x bar is equal to 1. Do you see that element? The element is this element. Right? So here this is 1. So let's look at this equation. Right? And if we just take the bar, reduce this equation, mod this ideal generated by f of x. So we have a of x, f of x. Okay, so this is 0 plus b of x, g of x bar. And so this is equal to 1. So in particular, this dude here, 1 over g of x bar, is b of x bar. So we just need to compute what this b of x is, right? And we have an algorithm for doing that. So that follows from the Euclidean algorithm. So this goes back to our problem. Okay, so the kind of spoiler thing here is that, I mean, not a spoiler, but okay, so we had these other methods that were not as good for maybe computing inverses, but we wanted to compute like what over 1 of alpha of x, what 1 plus 1 over alpha was in this particular field extension. Okay, so so we take a root, right? So let me go back. So let's go back to the problem at hand. So again, so back to the problem. Back to motivating question. Okay, so we took alpha. So let me write it like this. So Q adjoin. So Q adjoin alpha. So this was isomorphic to Q mod x, or Q adjoin x modulo. So we had x to the fifth plus 4x plus 2. So that was our polynomial. So that was this part here was f of x. Let me just check that that was the same polynomial, that I didn't have minus signs. Go back. Yeah, 4x plus 2. Okay, so that's what we had. And we wanted to compute what 1 over alpha was. And we go back. Okay, so under this correspondence here, so 1 over alpha, well, 1 over 1 plus alpha. So this thing corresponds to 1 over 1 plus x bar. Okay, so given what we said on the previous thing, so we need to compute the GCD of f with that element. So we need to compute, so we compute the GCD of 1 plus x and x to the fifth plus 4x plus 2. Okay, and to do this, we use the GCD algorithm. It uses the Euclidean algorithm. So what we'll do is we just kind of explicitly compute this, x to the fifth 4x plus 2. And I don't know how long this is going to be. I should have maybe done this. And I'm going to write this in the correct order. Okay, so we have this. This is x to the fourth. So this is x to the fifth plus x to the fourth. Okay, so now we have negative x to the fourth plus 4x plus 2. Okay, so now I write negative x cubed. So then we get x to the negative x squared minus x cubed. Okay, so we get the same thing again. So now we have x cubed plus 4x plus 2. All right, we're gonna get the same thing again. So then we have minus x squared, or let's see, plus x squared. So then we have x. So we're subtracting here. So we'll go up here. So we have x cubed plus x squared. Okay, then so once we subtract them, then we get a negative x squared plus 4x plus 2. All right, so then we have a minus x. So then we have a minus x squared minus x. Okay, so then this becomes 3x plus 2. And then we have a plus 3. Okay, so then we get a 3x plus 3. And so then this becomes a minus 1. All right, and so this one's not divisible anymore, so we now have a remainder. So so let's write this out. Okay, so we use this, and we had so x to the fifth plus 4x plus 2. So this was equal to this thing in the numerator. X to the fourth minus x cubed plus x squared minus x plus 3. All right, we have that. Then we do, so that was times x plus 1. And then we had a remainder of minus 1. All right, so this is what we had. And so this tells us that, right, so that if we take the quotient of this thing, so then we have that, so this implies that 0 is equal to, okay, so let's just write it in terms of alphas. Alpha cubed plus alpha squared minus alpha plus 3. Right, and then we have alpha plus 1 minus 1. And so this tells us that 1 is equal to these two things. So So it's all right. So it's equal to alpha to the fourth minus alpha cubed plus alpha squared minus alpha plus 3. And then we have alpha plus 1. Okay, so the point of this is that we now computed our thing that we wanted to compute. And that is that 1 over alpha plus 1 is equal to alpha to the fourth minus alpha cubed plus alpha squared minus alpha plus 3. Okay, so we computed the problem that we wanted to at the very beginning, and the idea was to use the division algorithm. So this gets a little bit more complicated. I mean, so here we got a little lucky because we only had to do one division. But in general, you'll get like a non-zero remainder here, and then and then you can so like if this was higher degree, you'll get something here, and then you have to take you have to divide this by this, right? And then you just kind of repeat, and then when you do the back substitution, you'll end up getting the expression that we want, which is this thing. So that the sum of the two things are the GCD. The GCD is always going to be 1. We proved that because this thing was prime, right? And this thing had degree smaller than the prime, and so it's impossible for them to have a common factor. The only factors of that are 1 or units in itself. All right, so that's how we can do the computation. There's a third way, and I might do that in another video. There's yet another way, and I might do that in another video.